The carbon of the carbonyl and the carboxylic acid right below it, again, above 150, right? 80 or so in the acid, and then you have a ketone, and then you have an aldehyde, and you will notice in those last two examples that the carbonyl of the ketone and the carbonyl of the aldehyde are both peaks that are above 200. That is a really distinctive peak because very, very, very few things actually show up that far downfield. So that sheet was really just to give you some sense that carbons do move over that whole entire chemical shift axis, and that sets you up for this. So here's a table that comes straight from your book, right? Here's sort of another way to interpret the same data. I think this way might be a little bit easier to look at. What I do not want you to do is to memorize these numbers, right? These are approximate chemical shifts. And so this right here is a carbon-carbon, well, the carbon of a triple bond. Doesn't matter if this is a carbon or a nitrogen, but because I'm looking at carbon. So the carbon here of a triple bond is going to show up between 65 and 85. That doesn't mean that maybe you have a peak at 89. And if you memorize these numbers, then you'll say that that peak at 89 can't possibly be a carbon-carbon or a carbon that's part of a triple bond. And that's simply not true, right? These are approximate values. Most atoms fall in these ranges, but not all. So if you do memorize them, don't be critical about where the range starts and where the range ends. Because you can see if you look down at this, the way that this same data is shown to you here, that really there's a lot of overlap, right? Regions really start to overlap each other. Here's the carbon-carbon double bonds and the aromatic rings, right? We talked about this. They overlap each other, so you can't tell me if you see a peak in this region, if it's a carbon double bond or if it's a carbon of an aromatic. You can tell me that it's not a CH3 group, right? Because the CH3 groups show up down here, right? And so I need you to become familiar with where certain types of carbons reside, where you will see them in a spectrum. I don't need you to memorize these numbers. And so what I'd like you to be able to do I would like you to be able to recognize that if this is 0 for TMS, that my alkane carbons are upfield, right? So these are carbon-carbon. And then maybe I have some carbon halogen. And then I might have some carbons bound to nitrogens. Right, maybe I'm out to about 40 now. And then between 40 and 80, I have carbons bound to oxygens, right? So this is a pretty distinctive region as far as chemical axis. Then, 80 to 100, that's approximately where I find my carbon-carbon triple bonds or my carbon-nitrogen triple bonds. And then I'm going to go 100 to 160. That's where I find my carbon-carbon or my arene carbons. Making this longer. Figure out where the video ends. Right, so then I'll put a 200 mark in here. And so from 160 to 200 or 170 to 200, you don't have to be critical. But that's where you find your carbonyls. That's where you find the carbon of a carbonyl. And so, again, you also can go 200 to 220. And here are carbonyls, but very specifically, this region is where you find aldehydes and ketones. Right? If you get 195, 200 and above to 220, that is a real signal that that is an aldehyde or a ketone. It's a carbonyl, but as a functional group, it's an aldehyde or ketone. So that means this region, right, also carbonyls, but this region is going to be carbonyls like carboxylic acids, or esters, or amides, or acid chlorides, or anhydrides. Right? We have lots of different carbonyls, but the ones that show up way downfield are aldehydes and ketones, and the others are in here. So if you see a peak at 185, right, you don't know whether it's a carboxylic acid, or whether it's an ester, or whether it's an amide. Right? You don't know that, but you do know that there's a carbonyl present in your molecule. And ideally, you can use other pieces of information to start figuring out exactly what that is. For example, if I give you a molecular formula and there's no nitrogen in the molecular formula, then you know that this is not an amide, right? Because if there's no nitrogen in the molecular formula, then that peak cannot be the carbonyl of an amide, right? So C13 in solving structures is often like a puzzle, and you have to put all the pieces together and think back and forth about what information you have and what could make sense. But this is what I want you to be familiar with, right? I want you to know that alkane carbons are up here, heteroatoms are in here, oxygens in here, triple bonds, double bonds, carbonyls, right? That's what I need you to be familiar with. So, in summary, let's say what C13 can tell us. Right? So C13 really tells us two really important, right? C13 spectra tell us, one, about symmetry. Right, so count the number of carbons in your spectrum. If there are 5 carbons in your spectrum, and there are 10 carbons in your molecule, then you know your molecule is completely symmetrical. If there are 5 carbons in your spectrum, and 7 carbons in your molecule, which you know because you have a molecular formula, then you know that you don't have a completely symmetrical molecule, but parts of your molecule must have some kind of symmetry. Right? So symmetry, you know, count the number of peaks. And then the second thing to pay attention to in a C13 spectrum is the chemical shift. Right? And the chemical shift, because you now have thought about where things fall on that chemical shift axis, right? That chemical shift tells you about the environment, or it'll tell you what kind of carbon that molecule or that atom is. Right? So chemical shift tells you about environment or what type of carbon, and the number of peaks that you see tell you about symmetry. So all of that said, let's practice some problems. You should have the next page in your notebook should be one that says exercise 1 on the top of it. And it shows you a spectrum that has 3 peaks. And it gives you the name of the molecule. 1-bromo, 2-methyl propane. So what I'm asking you to do is to draw this molecule, 1-bromo-2-methylpropane, and then to tell me which one of these peaks represents which carbon in that molecule. So go ahead and pause the video, draw 1-bromo-2-methylpropane, and think about which one of those carbons represents which one of those peaks. Pause. So unpause if you need to. Make sure that you have properly drawn 1-bromo-2-methylpropane. If you don't, then it will be impossible to do. So if this is my 1,2,3 propane, this is my 1-bromo-2-methyl. I'm going to go ahead and label, for simplicity's sake, I'm going to label that as carbon A. I'm going to label that as carbon B. And I do recognize that these two methyl groups are the same as each other. So I'm just going to label them C. And so I expect to see 3 peaks. I do see 3 peaks. I have a peak at about 21 ppm, peak at about 31 ppm, and a peak about maybe 42 ppm. And so the easiest one for me to recognize in this molecule or in this spectrum is that carbon A is bound to a heteroatom. Right? Carbon B is just bound to carbon, 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 and hydrogen. And carbon C is just bound to hydrogens and 1 carbon. Right? So B and C to me are alkane-like carbons, but carbon A is bound to a heteroatom. And I know that when I put a heteroatom on my carbon, that it pulls that carbon downfield. And so of these 3 carbons, the carbon that's furthest downfield is going to be carbon A, so the one at about 42. And then B and C. Well, again, how do you determine B and C? The truth is, B is a little bit closer to the heteroatom, so that's going to be B, and the last one, the one upfield around 21, is going to be C. Some of you might say, oh, these peaks are differently sized, which is true, right? And so you might say, well, C is really 2 carbons, and so I would expect the taller peak to be the one that represents 2 carbons. And sometimes that works. Sometimes it doesn't, right? So in proton NMR, we call that integration, and it really does work in proton NMR. In carbon, it sometimes depends, so don't rely on it, but certainly in this case, you could have used it. Okay. I don't tend to rely on that. I tend to pay attention to chemical shift and structure of my molecule. All right. The next question, there's no spectrum for the next question, so you don't have a page in your notebook. So the next spectrum says, take these 3 molecules and simply tell me how many carbon resonances you would expect to see. I'm going to draw this again lower. But how many carbon resonances or how many peaks would you expect to see in the spectrum of this molecule? So you're just giving me a number. See that, and I'll write C right here. Okay, so once you draw those, or go ahead and pause the video and draw those molecules, and then tell me how many different carbons you would expect to see in the spectrum from each one of those. So pause. The answer here would be 4. 1, 2, 3, and this carbon right here would be 4. And then for C, I would see 2 carbons, 1, 2, different from each other. I'm just highlighting them here. There's only 2 carbons in molecule C. So a lot of times people say 3, but remember chlorines don't show up. You're only looking at carbons. And then in sample B, it turns out that there's a plane of symmetry that runs through here. You're going to cut the bromine in half, and you're going to cut this substituent in half. And so 1, 2, 2. Turns out that that is the same as that because of the plane of symmetry, and that the square is the same as that because of the plane of symmetry. And then don't forget that I have some carbons here, so sort of a bullseye for that carbon, and then a heart for that carbon. So in this case, I would see 1, 2, 3, 4, 5, 6 carbons in the spectrum. The other thing to think about is where would you see these carbons? Right, so I'd see this carbon downfield in the 170 range. Right, I'd see these upfield in the alkane range, and I would see this carbon bound to an oxygen anywhere between 80 and 40. In C, right, again, that's a carbonyl of a carboxylic acid, so it's going to be somewhere between 170 and 120. And here's a carbon that's bound to 2 chlorines, which pulls it a little bit further downfield than 1 chlorine, right? That's going to be, I don't know, 60, 80, somewhere down there. In this case, I have 1, 2, 3, 4 aromatic carbons. So these 4 carbons, 1, 2, 3, 4 different carbons in here, would be found in my 110 to 160 region. My carbonyl of a ketone, right? Recognize that that's a ketone. So this carbon would be somewhere 200 or above. And then I'm left with the methyl group, and again, that methyl group is going to be the furthest one upfield. All right, we're almost done. Now you have the next page. You have a spectrum that says exercise 2 and 3. And so this is another way for me to ask a question. I'm trying to look at your spectrum. It needs to be a little lower. But you have this spectrum in your notebook, so look at it. Right? And here is a multiple choice question. So you have answers A, B, C, D, or E, right? How do you go about solving a problem like this? Right? Again, there are multiple ways, and you should do multiple things. First of all, when you look at your spectrum, count how many carbons you see, right? What do I see? And so in this case, I want you to pay attention to the peak out here around, I don't know, 210 or so, right? It's above 200. That little peak here is a real peak. And so when I look at the spectrum, I see one peak here, then a second peak here, and a third peak here. So I'm not seeing TMS in this case. So this molecule is going to have 3 different kinds of carbons because there are 3 peaks. Then what I do is I go through my choices and I look at this molecule and I figure out, well, if I had the spectrum of molecule A, I would expect to see this number of carbons in my molecule. So I want you to go through and tell me how many carbons you would see in the spectrum of A, B, C, D, and E. And once you've done that, then look at those, that data that you collected, look at your spectrum, look at your number of peaks, look at your chemical shift, figure out what the correct answer is. So pause and work on this. Honestly, if you don't pause and work on it, you have to struggle with these before you really start to understand them. Okay, you're back? So, first we're going to go through the number of carbons that you would expect to see for each one of these choices. In this case, I would expect to see 1, 2, 3, 4, 5, right? These three methyl groups are all the same. So 1, 2, 3, 4, 5 carbons here, so I know it's not A. For B, I see a plane of symmetry through here. I also see one through there. So I would say there was 1, 2, 3 carbons. Woo, 3 carbons that I would see in the spectrum of B. In C, these two are the same. So 1, 2, 3, 4, 5, 6 carbons for C. In D, plane of symmetry here, symmetry here. I would see 1, 2, 3. Ooh, 3 carbons again for D. And then for E, these two ethyl groups are the same. So 1, 2, 3, 4, 5. So I'd see 5 carbons for that aldehyde. So right now I can cross out A, C, and E. Now I have to choose between B and D, and I'm going to look at my spectrum closely. I'm going to look at chemical shift. These peaks are upfield. This one is way downfield. So if I have a peak above 200, I know that that's either a ketone or an aldehyde. And so ketone, no aldehyde or ketone, ketone, aldehyde, ketone. And so when I look at this, right, I'm looking at really B or D because they both had 3 carbons. I can toss out sample B because there is no ketone or aldehyde, and so clearly my answer has to be D, right? It has both the correct number of carbons in the spectrum and it has the correct chemical shifts. So my answer to exercise 2 is D. And so now you can do the last exercise. Right, and that is number 3, which is the same kind of problem. You have a spectrum, and you have 4 choices this time. So if I were you, I would go ahead and go through and say, how many different peaks would I see for molecule A, molecule B, molecule C, molecule D? And then I would go through this spectrum and say, how many peaks do I see? What are their chemical shifts? Figure out what it is. Go ahead and pause the video now so that you can figure out what the answer is. You get to see my mug. And now we're back. And when you think about these molecules, I would expect to see 1, 2, 3, 4 different peaks for A. I would expect to see 2, because I see a plane of symmetry here. So 2 peaks for B. In C, 1, 2, 3. And in D, 1, 2, 3. So I can toss out, and since I do see 3, I can toss out A and B, because they don't have the right number of carbons. And I think one of the telltale signs here is this peak right here, right? It is a carbonyl, right? It's above 150, below 200. And so that tells me that this is not a ketone or an aldehyde. So when I look at my 2 choices, this is an aldehyde, this is an ester. That ester carbon there is what I would expect to see here. The aldehyde, if it were this molecule, this carbon would be way down here, and it's not. So it's not C. The correct answer is D. This carbon's also pulled down to about 52 or so, which is the carbon bound to the oxygen. We know that pulls it downfield. This carbon here is the upfield carbon. Whew! So that is C13 NMR, right? It's a lot. You have to think about symmetry of molecules. You have to think about chemical shifts, right? You have to think about a lot for these molecules, right, to solve them. But when you solve them, you know every single piece of data matches what you expect. So there is an NMR assignment, right? The next page is in your notebook. So it looks like this, C13 NMR assignment, right? There are 4 questions. So I would like you to go ahead and answer those 4 questions. That's your NMR assignment. That is due when you come to meet with me to actually use the NMR spectrometer, right? So that's when that is due. It's on your syllabus. And so you're going to write out, I'll post this on Blackboard again for you, and then you can simply write out the answers that you need to write out the answers for. There's one more piece of information that we need to go over, and that is depth spectroscopy. But I'll go ahead and make that a whole separate video for you so you can keep them. It is a type of C13 experiment, but we'll go ahead and pause this one for now because I can see that it's getting to be a long video, and I don't think YouTube likes totally long videos. So you do need depth spectroscopy before you can answer all 4 of these questions. So I'll go ahead and make that now after I pause this one. All right, see you soon. Peace out.